Thomas Young did a famous experiment called the double slit experiment that provided incontrovertible evidence that light was a wave. And he first demonstrated interference of waves in other situations, for example, waves on water. If you imagine looking down on the surface of a pond, and say you drop a rock in the pond, and you know that waves spread out in a circular pattern. Well, say you have something that's constantly tapping on the surface of the pond. So you're getting this constant series of waves spreading out from one point. And say you put another source of waves at another point in the pond. And so you have another set of waves emanating from this point. Well, when the waves from one cross the waves from the other, they add up at that point right there to make a larger wave. So this would be a point right here of what we call constructive interference. One wave adding up with another to make a larger wave. And you could have one wave adding up, say the peak or crest of one wave right along here, coinciding with the trough of another wave. And so at a point right there where the crest of one crosses the trough of another, they would cancel each other out. And that's what you would call destructive interference. And you can see this characteristic interference pattern. You see the pattern formed right in here. That's characteristic of wave interference, of a wave from one source interfering with a wave from another. You get a pattern that looks like that. Now, what Thomas Young did was this. He set up a little wall with two small slits in it. And then he had some light shining in from over here. Well, when the light went through this slit, if you think of the light as a wave, it turns out it's not like a particle. It's not like shooting a bullet and it just flies through the slit and keeps going. The wave comes out of here, and it's a wave similar to the wave coming from a point source on the surface of a pond. And then the light coming through the other slit came out as a wave and spread out there. And you got this interference pattern. Some places where the light waves are overlapping and you're getting a constructive interference, the light waves adding up to a larger wave, and some places where you're getting destructive interference. And he had another wall over here, and the light would land on this wall, and where you would have places of constructive interference, it would produce a bright spot on the wall. And where you would have places of destructive interference, the crest of one wave coinciding with the trough of another, you would get a dark spot on the wall. But the point is, you would get this interference pattern, and you could see the results of it in light and dark areas landing on this other wall over here. So light was seen to be interfering. And as we said before, interference is something that only waves do. So light here was definitely seen behaving as a wave. And this experiment was fairly easy to reproduce, so other scientists were able to produce the same result. And scientists gradually began to believe, based on evidence such as this, that light was a wave. And light was shown to do other things that only waves do. For example, diffraction. Diffraction is the bending of light around corners. If say here's the ground, and say here's an object, maybe the edge of a table or something, and light is shining down, and we'll think of it as a wave coming in instead of a beam. Think of it as think of these as the waves on an ocean rolling in on the beach, but instead these are light waves shining down on the earth. Well, the light's blocked, and so you end up with some light landing down here, and over in this region you get a shadow. But the light isn't completely blocked. It bends around the corner a little bit. Now what I've drawn here is exaggerated. It doesn't really bend that much, or at least you can't notice it with your eyes that much, but it does bend around corners a bit. That's called diffraction. You know that waves do that because you experience sound waves doing that all the time. If you're in one room here in your house, and say you're standing right here, and say your friend is standing over here, and you talk, well, sound waves come out, but they can go right through here and bend through that opening a little bit. Someone can still hear you in another room, even though they can't see you. The light waves don't bend nearly as much. How much they bend has to do with the frequency and the wavelength, but they do bend around corners. And one thing you can notice is that as a result of diffraction, shadows don't have well-defined edges all the time. The shadows, or the edge of the shadow, will be a little bit fuzzy, and that's because some of the light is bending a little bit as it goes around the edge. The point here is that diffraction is something that waves do. Particles don't do this. If you're shooting bullets in this direction, a bullet would either miss and land there, or it would hit and stop. But it wouldn't go here and bend around like that. Particles don't do this. Only waves do. And light was shown to do this. So the point here is that light was shown to do things that only waves do, such as the interference in the double slit experiment and diffraction here. So this was the situation. Newton had said that light was a particle, and then Thomas Young came along and said that light was a wave, and Young produced experiments showing that light was a wave. And over the course of the next century, over the period basically the 1800s, experiment after experiment after experiment was done showing that light was a wave. And gradually people began to disbelieve Isaac Newton's particle theory. And by the end of the 1800s, it was basically universally accepted among scientists that light was a wave. And Newton, as great as he was considered to be, was seen as wrong on this point. Scientists understood that light was a wave. They could prove that light was a wave, and they had all read about, and many of them had done these experiments demonstrating that light was a wave. So even though Isaac Newton was still greatly revered, he was seen as wrong on this particular point. And that is until the year 1905. In the year 1905, another physicist came along and did an experiment that clearly demonstrated that light is a particle. And the experiment was known as the photoelectric effect. And the physicist who did this later received the Nobel Prize for this work. And the Nobel Prize is the most prestigious prize that anyone can receive in physics. And the physicist who did this was Albert Einstein, a name I'm sure you have heard. If there's anyone that was more of a genius than Newton in the field of physics, it was Einstein. And he produced this experiment showing that light was a particle. And he called a light particle a photon. So instead of a corpuscle, we have a new name for it, a photon. But what we have here is a situation that is just absolutely extraordinary. We have the entire scientific community globally firmly convinced of one idea, that light is a wave. And there's basically only two people saying that light's a particle. But those two people happen to be Isaac Newton and Albert Einstein, the two greatest physicists who have ever lived. So normally when all the scientists agree on one thing, it's generally well accepted as a scientific fact, especially if it's been verified experimentally. And if there's a couple of people disagreeing with it, well, you just wonder, who are these guys who are disagreeing with all of the scientists on the planet? Well, in this case, these two guys are Newton and Einstein, people worth listening to, especially when you're talking about physics. So what do we make of this? Is light a particle or a wave? Well, today scientists recognize that light simultaneously has two different natures. It behaves as a particle and it behaves as a wave. And in some experiments, the wave nature of light shows up. The experiments that Thomas Young did are valid. Those just happen to be experiments that demonstrate the wave nature of light. And the experiment that Einstein did happened to be an experiment that demonstrated the particle nature of light. But they're both considered valid today. Scientists don't really completely understand it. We don't claim to really know how this can be, but we just accept the fact that light behaves as a particle and it behaves as a wave. Sometimes you hear the phrase wave-particle duality. And that's just a term to point out this dual nature of light. And that's another term you hear, the dual nature of light. It behaves as both a particle and a wave. And sometimes you see the word wavicle, which is just they're trying to make a clever combination of the word wave and particle. That's not really common, just more of a catchy term. But scientists have accepted this fact that light behaves as both a particle and a wave. And in some experiments, the particle nature is more clearly seen, and in other experiments, the wave nature of light is more clearly seen.